Okay, so I want to give you an inside perspective on some stuff that happened at Mozilla. You see, when I started at Mozilla 7 years ago, we were in a very different place to where we are now. We'd been used to being the fast, more stable, more secure alternative to the incumbent browser, and then times changed, and another browser came along, Chrome, which had a better security architecture, was simpler, and therefore was easier to tune and was faster. And that was very difficult for us. It was a difficult time. And in particular, from my point of view in security engineering, we weren't leading in security in the way that we wanted to. So that was hard. But we're in a different place now. We're now in a place where we have very much closed that gap between our browser and other browsers. We've made the same architectural changes that we needed to make, that we were prevented from doing for a long time because of things like our old add-on architecture and things like that. And we've moved to a place where, we've pretty much closed the gap in all areas. And not only have we improved a lot on the security side of things, most tests say that we're faster than the competition, and that's great. And I want to take you on part of that journey, from where we were then to where we are now. And I want to take you on that journey from the perspective of where I sit in cryptographic engineering at Mozilla, because for some people, probably Scott, maybe some other people, that's an interesting place in the organization. And along that journey, I want to do three things. Firstly, if you're new to hearing about the web PKI and the cryptography in your browser, you'll learn some of the building blocks that allow your browser to connect to sites securely. How many of you does that apply to? Who's new to this sort of thing? Okay. Secondly, you'll understand some of the things that Mozilla has done and is doing now in working to ensure that the web you use is secure, stuff like Let's Encrypt, that sort of thing. And also, I'll give you a little glimpse of what's coming up further on down the road. What are we doing now that's going to improve things in the future? Now, why should you listen to me? I'm a software engineer. My name's Mark Goodwin. As I've mentioned already, I work for Mozilla on Firefox. And in the 18 years I've been in the software industry, I've been very fortunate. I've been able to work on building things. I've been able to work on breaking things. I've been able to work on defending systems from attack. And in the course of that work, particularly in the last 13 years when I've worked on security stuff, I've been really lucky to work on some really, really interesting things. And who's heard of same-site cookies in here? Okay, so that was my thing. I invented that with a colleague at Mozilla and specified it with a compatriot at Google. And a few of the things we're going to look at this evening, I was lucky to get to before anyone else as well. So that's pretty good. Why should you listen to me? What's in it for you? I've been at Mozilla for a long time. 7 years is a long time in technology these days. And there's one thing that's kept me there. It's that Mozilla has a perspective on the work that they do that really appeals to me. And some people might think, well, it's the Mozilla mission. Mozilla works to ensure that the internet is a global, open resource that's public to all and accessible, and that's great. But it isn't that. There's a fearlessness about Mozilla. And Mozilla keeps on going when other people might have abandoned the fight. It's not good enough to catch up. Mozilla likes to get ahead. And there's a joke at Mozilla that the most important release that was ever made because of us was Internet Explorer. Internet Explorer 7, because we forced Microsoft to reband the team that they'd disbanded when they finished Internet Explorer 6. And they then had to start building browsers again. And it's the fact that it's not good enough to be where we are now. And that's what I want you to get out of this. I want to give you some of that courage, that fearlessness. I want you to be able to look at the systems that you look at day to day in the course of your work and to say, well, actually, this is the way things are, and not just shrug and say, well, that's how it is. I want to give you the courage to actually fix things. Because fixing the internet's hard. There are billions of people using it every day, and people tend to whine when you change things under them. But we've done a bit of that. Scott's laughing, he knows what I'm talking about. Okay, so security. There we go. Pro tip, don't talk for longer than your lock screen timeout. Okay, so I'm going to be talking about the Web PKI. Specifically, I'm going to be talking about certificates and how we revoke them. So from the lack of hands up earlier on, everybody here knows what I'm talking about when I say certificate, right? Yeah, pretty much everybody knows what I'm talking about when I say certificate. Now, I want to think about the trust properties that this gives you. You know that thing where your presentation software shows you what slide you're on and stuff? It isn't doing that. Oh well, I'll do that turning around thing. Okay, so they allow you to to verify the identity of an entity. Let's say it's a website. If you go along to scotthelm.co.uk, for example, you know it's Scott's server that you're talking to. Why do you know it's Scott's server that you're talking to? Any idea? It's got a certificate. Okay. It's got a certificate. It says, this is scotthelm.co.uk. And the bit that's important from the technical perspective is that this certificate has a public key that corresponds to a private key somewhere on a server. And as part of the handshake between your browser and that server, you can cryptographically prove that that server has one half of the key pair that you've got the other half of in that certificate, right? And you trust these certificates because some authority has verified the identity of the thing that you're connecting to. In this case, the server at that particular domain. Okay, and you trust the authority because your browser trusts the authority. There is some work that's gone on to establish that this certificate authority is in a position to verify identities, and implicitly, because you trust the browser to trust the certificate authority, you're also trusting the browser, right? You sit down, you open Chrome or Firefox or Microsoft Edge or whatever browser you use, and you trust that they're doing the right thing to ensure that the certificate authority is doing the right job, okay? And, you know, if you follow at all the Mozilla policy lists and you see the things that go into deciding who's in and who's out in the root certificate program, you'll actually see a lot of these discussions taking place. I was involved in some really fun discussions last year when we decided that we didn't trust WoSign and StartCom anymore. And there's a very interesting meeting I was involved in where we had to tell a company that was very much larger than we were that actually we weren't going to let them do their thing anymore. So that gets kind of interesting. Okay, so that's how it works. But the key thing about this is that this is a relationship that once you have established the trust, because of the way it's established cryptographically, via a chain of certificates chaining to a root that your browser trusts, once you have that trust, you can't get rid of it. Okay, you've got that trust there. It's a mathematical proof, if you like, that the server has the private key, that the certificate has been signed by the certificate authority, that the certificate authority is issuing certificate has been signed by their root certificate, and that the root certificate exists in the browser's built-in certificate list, right? It's either there or it isn't. It's a binary thing, and you can't undo it once it's there. And that brings you to the problem of revocation. But before we get to that, I want to think about the trust in terms of a real-world thing. Let's think about, for example, your driving license. Okay, who drives? Okay, and you get your driver's license from the DVLA, right? They're an authority. They say, these are the vehicles and these are the people that are allowed to drive them. Okay, so they're very similar in analogy to the certificate authorities that we deal with for this trust on the internet. Okay, now I want to think about the process of getting banned from driving. Yeah? Who's had a driving ban? You don't have to tell me that. It's okay. Who's had points? Okay. Anyone who's had points, what did you have to do when you got points? You had to pay some money. Did you have to do anything else? Training course. What did you have to do with your driver's license? You had to send it back, and what did they do to it? Well, what did they do to it? You got a little thing written on it saying you're a naughty boy, don't do it again, right? Okay, so you've got a physical document there, and you can modify it to say, actually, it used to be a person with a clean sheet as far as driving is concerned. I don't want you to treat them like that anymore. Now, we can't do that with certificates, because the certificate is there. The certificate can be copied many times. You can't recall every collection of bits that you've sent out to different clients and, right, this server's been a naughty boy on it, can you? So we have to deal with some of these things in different ways. Okay, so before we actually think about the mechanics of revocation, let's think about a bunch of things that can go wrong. Who remembers Heartbleed? Yeah, so there was a OpenSSL vulnerability, and it allowed you to dump out bits of memory, and you could build up the server's private key by inspecting what came back. What's the problem with that? You can imitate anyone. If you've got their private key, to all intents and purposes, you can prove that you are them, right? Okay, and does anyone remember what happened as a result of that? Mass revocations. Yeah, there was a mass revocation event. Lots of people had to go away and revoke the certificates they had that would have been fine otherwise. And that's bad, right? But there are more ways than just your key being compromised that mean that your certificate might need to be revoked, or a certificate might need to be revoked. What happens, for example, if a certificate authority issues a certificate to you that they should not have done? What if I do a really good job of impersonating Scott Helm? What if I go and I manage to convince them with my fine English accent and my elite hacking skills that I should have his certificate, and they give me a certificate for scotthelm.co.uk? That'd be bad, right? Unthinkable, right? Well, it happens. I haven't done it to Scott, should make that clear. And I wouldn't admit it if I had, I should make that clear as well. But this happens. You have these authorities, and their job, their one job, is to validate the identities of entities so that they can issue certificates to them, and sometimes they get that one job wrong. Okay. Or what happens if it's not an accident? What happens if a certificate authority is doing its job quite well? They're not misissuing certificates inadvertently. They've got a good handle on all their processes and their systems, and then one day some people in black suits turn up and have a little chat with the boss. Okay, again, it's unthinkable, isn't it? But it's happened, right? We know of instances where this has happened. And so even if the certificate authority wants to do a good job, even if, as far as the processes and procedures and the audit trails on top of all that say that everything's going well, there might be circumstances in which they are forced to do the wrong thing. Or what if their systems are forced to do it without them knowing about it? What if someone breaks in and effectively compels issuance via technical means? Or even worse, what if they get their core systems breached, somebody owns the HSM that the keys live on, and they can sign anything that they want and appear to be that CA? All of those things sound completely unthinkable. All of those things have happened. All of those things have happened in the last few years, actually. Okay. Now, before I did this talk, somebody tweeted me and said, somebody tweeted Scott actually and said, "Scott Helm, someone's doing the talk that you did last year at SteelCon." And I looked, and his talk had exactly the same title pretty much. And I had a look, and it was really good, so I had to make mine different. I actually recommend that you watch that talk, because Scott goes into a lot of the technical detail that I'm deliberately not going into. I want to think about this less in terms of the actual nuts and bolts of the technology, with an exception of a bit at the end, which is new. And I want to think in terms of this trust, okay, and how you distrust, how you revoke that trust relationship. Okay. And I want to think in that way while we go through some of the history of the technologies that have appeared over the years in this space. So the first thing we have, let's play Acronym Soup. Who knows what CRL means? Certificate Revocation List. Okay. Now that's exactly what it is. It is a document which is a list of certificate serial numbers that pertain to an issuer, a certificate authority, and it is signed cryptographically, so you can make sure that the CRL comes from the people that issue those certificates. And it tells your browser that all of the certificates in this list are bad. Okay? Simple idea, and it's fairly simple in its execution, but it has some drawbacks, and we're going to talk about those in a bit. One drawback that I'm going to talk about now is the fact that each certificate authority can have its own revocation points and can choose how it does that revocation and how browsers have to fetch that. And we'll talk about that again, all being well, in a minute. So CRL, in practice, turned out to be a bit cumbersome. Certificate revocation lists can be very big. They can take a long time to download. When you download a new version, you have to download the whole thing. And in practice, actually, very few browsers have ever actually shipped with them turned on. In some enterprise systems, people have their systems configured to require CRLs for certain websites, but it's a rare thing. It's always been a rare thing. So we realized this sucked, and we came up with OCSP. OCSP is Online Certificate Status. Oh, sorry. Can anyone tell me what OCSP stands for? Interaction. I did it already. Online Certificate Status Protocol. Okay, and it's you get a yes/no answer from a server on whether or not a particular certificate is still valid. And it's a kind of a weird thing because actually you are functionally treating your certificate as if actually the real thing is a separate short-lived certificate with its own signature, which led to all sorts of arguments when we tried to get short-lived certificates standardized in the CA browser forum, and the CAs didn't want us to, and we said, well, you're basically doing this anyway. Anyway, digression. And then this presented some problems, notably the fact that it increases the latency of connections quite a lot because you explicitly by design have to go and fetch these statuses every time you make a connection that uses a particular certificate, and you have to do that for every certificate in the chain, right? You can't just do it for the end entity. You also have to do it for the issuer and any other certificates that might be in that chain to be sure that everything's okay. So it increases latency, and it kind of has to fail open for reasons of performance, but also availability. You don't want your site to be taken down because the CA's OCSP responder sucks. And it turns out that your CA's OCSP responder almost certainly does suck. And so Google stopped doing OCSP, and they started doing a thing called CRL sets, and we started doing a thing called 1CRL, and Microsoft started doing a thing called CTL, and they're all basically the same thing. They are ways of doing a CRL-like thing, but centralizing it and getting it from your settings infrastructure from the browser vendor. So it's a proprietary way of doing a CRL type thing. But importantly, it has the same scalability limitations that CRLs have. They scale order n with respect to the number of certificates in the ecosystem, which is to say they don't scale well at all. And then OCSP must staple is like OCSP, except you staple the OCSP status to the server hello as part of the TLS handshake. So it's always there. So in theory, it matters less if your CA's responder is down because you got one earlier and it's still good. Okay. And OCSP must staple uses the TLS feature extension in X509 to make sure that that happens. Okay. So that's how that works. Now, CRLs and the newfangled replacements, proprietary replacements, have the property that if you have an active attacker between you and your destination and you and your CRL providers, you can actually fail closed. If your CRL hasn't updated for a while, or your 1CRL data hasn't updated for a while, it's really noisy. No signal. It's really noisy. What happens is you won't have up-to-date data on any of your sites, and therefore you can say to the user, bad things are happening, don't keep on talking to this site. Okay. Unfortunately, the drawbacks mean that they don't work fantastically in the real world. OCSP must staple are better. OCSP has some privacy issues. OCSP stapling is better. OCSP must staple adds an additional level of security to this, but they have the fundamental problem that you can implement OCSP must staple if you like, but if your attacker is doing something different and they've got a misissued certificate, they're not required to turn this on at all. Okay. And so various things have happened over the years to help the visibility of, to help with the prevention of certain types of attack, and also to help with the visibility of them. So in terms of prevention, HPKP was a nice idea. Did people know what HPKP was? Yeah. So HPKP was a way of, you could, from your website, configure it to say, next time you visit this website, unless the public key, unless the public keys here are listed among the certificates in the certificate chain served by the server, then don't connect. Okay. Really powerful, because it means if someone misissues or is compelled to issue a certificate for your site, you can say, actually, I don't trust this. It's pretty powerful in that respect. Unfortunately, it's also a feature that can be misused, and we started seeing a lot of denial of service via bogus HPKP headers. But that's a different story. We can maybe talk about that later if people have questions. So Chrome, I think, have turned this off already. We're planning to do so soon. CAA, Certificate Authority Authorization. This is a DNS record that tells you which CAs are allowed to issue for this particular domain. That's a cool thing. It's something that certificate authorities have to comply with, and not something that your browser sees, but it adds a process step which you can hold CAs to if you notice that they're not doing it properly, which might result in them being pulled from a root program if they don't do it properly. And CT, Certificate of Transparency, Scott mentioned it in his talk earlier on. The short version of it is a cryptographically assured way of having a transparent log of all certificates. And blockchain, yay! Merkle hash trees. Do you shoot people that say blockchain? Is that what happens? I've got a t-shirt that says, don't talk to me about blockchain on the back and crypto on the front. So if people say, oh, cryptocurrencies, I can go. Anyway, so CT is a really nice idea, because if anything happens that results in a certificate being misissued for your domain, whether it be by neglect or by compulsion or by the certificate authority being owned or whatever, you can get information on that, and that's good. Most of the time. It doesn't help you against really targeted attacks, but again, we can talk about that later if you're interested. Anyway, so what does this tell us? It tells us that actually, in terms of the properties that we want for our revocation, what we're using at the moment is only a partial solution. The closest we've got to exactly what we want is must staple, but it would only work if everybody in the world used it. It would only work if we compelled, as part of the baseline requirements, all new certificates to be issued with must staple, and all browsers supported it. Unfortunately, the only person in the world to have implemented OCSP must staple is me, so you can only get it in Firefox. Chrome haven't implemented it because there are problems with the OCSP stapling implementations in popular web servers. Apache and Nginx both have issues, and because of that, they deem it a dangerous feature to implement, because they think that people will break their systems by turning it on. So that's a shame. We're in a situation where the best tools that we have aren't quite good enough, and some of the good tools that we had, like HPKP, are broken in fundamental ways, and we'd have to go through another round of standardizing things to fix it, and that's bad. So what can we do about it? Well, we need to be innovative about how we fix some of these problems. Apple have done a really good thing. Who knows what Safari does to do its OneCRL-like functionality? Anybody looked into this? I expected at least one hand there. Okay, so Safari rather than having a 1CRL-like mechanism for every single certificate that they want to revoke, say, okay, we can't make a data structure that can store all the things we want to encode fit in a client's user profile. Why don't we have a Bloom filter to store that information? And if we get a hit on it, rather than assuming that that certificate's been revoked, we'll actually go and then do a check, right? That has the advantage that the data that goes to the user's browser is actually pretty small, and that you only have the hit of the round trip to the online status check for cases where it looks like it's bad. Who knows about Bloom filters? Do you know what a Bloom filter is? Yeah? Okay, so I'm going to do a little bit of computer science when I've logged into the thing again. This is why you practice talks, people. I've got an excuse. I've been in hospital most of this week. I got knocked off my bicycle. And so I wrote my slides on the way here. So if I sound a bit breathless, it's because I've got a fractured rib and a punctured lung. True story. So Bloom filters. Who can tell me what a hash function is?
It allows you to take a piece of data and you can take a digest of it, a smaller representation of it that should be unique, and you can't reverse it back to the original.
Okay, so it allows you to take a piece of data and it maps it to a smaller piece of data, right? So in a cryptographic hash, it's important that it's almost certainly unique, and it's important that you can't get back to the original thing. But hash functions in general are mostly about making sure that you can take something and it always maps to a particular value of something else, okay? And that generally, if you have various somethings, you can't easily predict what the output's going to look like, okay? So imagine we have a hash function which takes strings like these and maps them to an 8-bit value, okay? So we take Anna, and it gives us that output. We take Anne, it gives us that output. We take Hannah, and it gives us that output. Let's go back a couple. No, I've messed up my slides. Okay, I'll put them in the wrong order. This is what happens when you write your slides on the way here. Okay, so we've got this way of going from a particular input, in this case a name, and taking it to a particular output. Okay, so let's say we take a list of all the names that we know and we make hashes of them, like I've sort of done there. And then what we do is we take a subset of the names that we're interested in. Okay, we're going to go for names which happen to be palindromes. What's a palindrome, people? There's a Monty Python joke in there somewhere, isn't it? Isn't that an acronym? Yeah, palindromes are strings that are the same forward and backwards. Okay, so what we're going to do is for all the strings that are palindromes, we're going to take the bits that are the output of hashing that and put them in a bit array at the top. Just make sure they're set. And we'll do that for all of the strings which happen to be palindromes, and we won't for the ones that aren't. Okay? And then what we can do is if later on we want to check to see whether a string might be a palindrome, we find the hash, and if all the bits for that hash are set in our bit array, we can say, yes, it's probably a palindrome. Okay? Now, probably is a key word here. So, rewinding, what Safari does, which is quite clever, is it takes a certificate, it hashes it, it takes the output, and it looks to see whether the output is in that bit array. And if the output is in the bit array, and it's a much bigger bit array than 8 bits, obviously, then it'll say, this looks dodgy, I'm going to check on this one. And it goes and does the check. And it means that the data is much more compressed. The difficulty is that it's only probably, and it means that you still have privacy problems, and you still can't fail closed because reasons. Okay. So let's talk about a way of fixing that. It's a bit of work that's been done by academic researchers that we spotted last year, called CRL Lite. And it builds on this idea of using Bloom filters, but it doesn't have any of the constraints that Bloom filters have, in that it is not a probabilistic data structure, it is deterministic. It allows you to take the revocation state of every single certificate that has been issued on the WebPKI ever and tell you deterministically whether or not it is revoked or not. Okay? And it's small. And Scott was talking in his talk last year about CRL sizes. There was a particularly big one. How big was it? 94 meg. Right, 94 meg for one CRL. For a single CRL, not one CRL. There's a one CRL joke up there as well. Anyway, I'm sorry. And we can get the revocation state for every single certificate in the Web PKI, all of them, every single one, in about 30 meg, with about 30k of updates every night. Okay, that's all right, isn't it? And what that means is we can update it in the browser every night. And if we don't get those data, if the data gets old in the user's profile, then we can say to the user, look, you're not getting your revocation data. You can't trust any website that you visit, right? So that's good. You're not getting the out-of-band connections back to an OCSP responder every time you make a connection, so there's none of the latency or privacy implications of that. And it scales well enough that anyone can be in this list. And actually what we do here is we take the set of certificates, we find all of the revocation points for those certificates, and we build this continually and ship it to the browser. Okay. And it also allows you to have incremental updates. So if you haven't been online for a couple of days and you connect, it will only get you the changes from when you last got the data to where you are now, rather than having to download the whole thing again. So that's pretty nice. And how does it work? Well, it uses Bloom filters. It uses a Bloom filter cascade. Who's heard of those? Okay, well, it's quite simple. So what you do is you take your Bloom filter. Let's go back to our original Bloom filter. That colour doesn't work very well. So here we've got Anna, which is a palindrome, Hannah, which is a palindrome, and then Marcus, which purely by luck and the fact that the input space is larger than the output space, happens to have bits that are entirely set in our Bloom filter at the top. Yeah, that would be a false positive. The Bloom filter would say that Marcus probably is a palindrome when clearly it actually isn't, right? So what you then do is you take that and you create another Bloom filter of things that look like they're positives but aren't, you know, false positives. And then you're still going to have some false negatives of your false positives. So you create another filter of false positives of false negatives of false positives, and false negatives of false positives of false negatives of false positives, and you keep on going until you haven't got any false things anymore. And that's called a filter cascade. And it's very small, like a Bloom filter, but here's the key thing, it's deterministic. It gives you a definite answer whether the certificate that you're looking at is in that set or not. And that, in a nutshell, is how this new thing works, this CRL Lite thing. Or 2CRL, as I might call it, because I have the dad joke sense of humour. And we're going to be testing that later on this summer or early autumn, and hopefully we'll be able to turn it on for users soon. Okay, so hopefully I've demonstrated that we've sort of closed a gap, because a lot of the new features that we have in the Web PKI happen with us first. Must staple we do, and no one else does. And this CRL Lite thing, the first thing that other browser people heard about it was when I talked about it at the CA browser forum a few weeks back. These, oops, ooh, didn't know it did that. Cool. So these are good things. A point I want to make about this is that a lot of this requires a whole lot of work. A lot of it requires change and flux and things that people are very happy with not having had changed. As I said at the beginning, what I really want to do is to point out that even in the most horrifically complicated systems with the largest number of uncooperative stakeholders, it's possible to push through change and make stuff happen. And really, you know, more than anything else, this talk is a rallying cry. Let's go and do this everywhere. So that's all I wanted to say. Do you have any questions? Sure, I had a thing there. There's meant to be a QR code so you can look at the slides later. Oh, there is, it just hasn't loaded because Google Sheets. There we go. Oh, no. I'll tell you what, I'll just move the other window over. There we go.
So I guess, how do you know which CRL endpoints to look at? Because you have the root store as Mozilla, and the leafs are issued by the intermediates. Do you have full visibility of all intermediates? Because the intermediates carry the revocation. Well, it's actually the leaf that carries the revocation, the CRL location. So I assume you scrape all of those and pull them all down and build the bloom filter off that. How do you ensure that you get full coverage of all CRLs?
So the baseline requirements say that every leaf should have a revocation point. And in theory, we can work off that. In practice, the internet is a messy place and everything's broken all of the time.
Just
so
to clarify,
we made
sorry, are you saying that so the Firefox client aggregates those from end entities that it sees?
We don't do it on the client, we do this at our end, at the services end. We build these lists on the server. So what we do is we look at CT data, so we've got every single certificate.
That's where you get it.
No. It's more complicated than that. Even if you use the CT data, this stuff is all very broken. You know, have a chat with Rob Stradling about this sometime. This data is all very, very broken. And we realized it was very, very broken, and it was hindering efforts for things like OneCRL. You get little things like, if you fetch a CRL for a particular certificate, in this CRL, the issue will be encoded using a particular set of ASM1 encodings. In the certificate, they'll be completely different. So you can't do a comparison on the two of them. So strictly speaking, they've complied with the baseline requirement that says you have a revocation point. However, you can't do comparisons and cryptographic proofs that everything goes back to the root because the data are different. Okay, so we modified the baseline requirements recently to ensure that all certificates authorities are disclosing all of their intermediates, all of their issuing certificates. And this allows for two things. One of them is that we can say, along with the requirement to disclose the issuer, they have to disclose all of the revocation points for certificates issued by that issuer. But also, we can say, because we have the full set of issuing certificates in the Web PKI, we can do some clever stuff like preloading them in the browser to stop things like AIA fetching having to happen, which is another slightly leaky privacy feature in the PKI. Does that answer your question?
Mark, oops, sorry, was a little bit too loud. So is there going to be a hard failure if something doesn't look kosher?
Yes, but is there going to be a hard failure? The internet is a messy place and everything is broken all of the time. My intention is for us to be able to do a hard failure in all cases except for cases where the user's profile data is older than the SCT relating to the certificate in the connection. Okay? In cases where the SCT is newer than your browser's data, there might be inconsistencies between your revocation state and the certificate you're actually looking at. Probably what we can do is we can say, because the certificate is super new, like literally a few hours old, it doesn't matter. What I would like to be able to do is to hard fail for all other certificates. So everything post the CT start up to the freshness of your data can be hard failed.
I mean, there's certainly the danger that you shoot yourself in the foot if something is going wrong.
So, as I mentioned, we'll be testing this. The first couple of versions that ship with this will have it turned on in report-only mode, and we will be monitoring the differences between OCSP responses for certificates and what would happen if we used this list.
If I may ask another question, what about Thunderbird, for example? It's a mail client at some certain extent, and also it supports POP and IMAP. Is anything planned?
So initially, Right, so the correct answer is the platform features will be available to the Thunderbird team, but it's not down to me to make sure that they get used. The other half of that argument is that the work we do around this related to baseline requirements are specifically for site identification. However, that does not prevent people doing clever things with the same techniques, and all of the plumbing will already be in the Mozilla platform. Scott?
Are short-lived certificates really that far away? Would that be the better solution?
The question is, are short-lived certificates really that far away, and would that be the better solution? My feeling from watching the debate inside the CA browser world for a while is that short-lived certificates are a long, long way away. Would it be a better solution? In my opinion, and admittedly I do have a dog in the race, OCS PIMA staple as a baseline requirement would be the best solution.
Are all certificate authorities, do they all kind of revoke a certificate at the same kind of like timescales and things? I mean, some CAs might revoke it within 30 days or so, so you've got a 30-day vulnerability window.
So it's specified in the baseline requirements, the time scale at which they're supposed to revoke following notification. Scott probably knows what that is, I haven't got a clue.
24 hours from proof.
There we go, 24 hours from proof, thanks Scott. I don't know how these things are supposed to work, I just implement them. Any more? Thank you.